Episode 4, Northwest Month 2022. Let's go.
Yeah, guys, like we always do, right? You try the problems out, then we correct.
Hey guys, check out the problem. If you can't, move on to the solution.
Question 4. Distinguish between a photon and an electron.
All right, so guys, right there, photons are massless and chargeless quantum mechanical particles, while the electron is a charged subatomic particle, which occurs in all atoms. Okay. Again, I think if you have just a moment to think about it, you realize that yeah, that's something probably something you've always known, but you've just never put them like that. B part says,
Account for the conservation of energy where a photon ejects an electron from the surface of the metal.
okay, so of course the famous Einstein's photoelectric equation, HF equals work function plus the kinetic energy of the ejected photoelectrons. So of course you realize in here that the energy of the photon is partly used up to do work in overcoming the electrostatic force of attraction that binds the electrons to the positive nuclei, and the rest of the photonic energy provides the kinetic energy of the escaping electrons. Okay, so part of the energy of the incident photon, which is HF, that's the complete energy, part of it goes to the what? To provide the work function of the material, which is basically an expression of how much work the photons have to do to overcome the electrostatic force of attraction that keeps the electrons bound to the positive nuclei. Okay, and then the rest is used up as the kinetic energy of the electrons. So that's what I've explained here. Okay, so we can go on and then look at
C.
C.
Light of wavelength 5.8 times 10 to the power negative 14 meters falls on the surface of a certain photoelectron emitter of work function 2.16 electron volts. Determine whether photoelectrons will be emitted or not.
All right, guys. So to determine whether we're getting photoelectrons or not, the first thing you have to recognize is that I've just written this work function. Notice that I've written this work function. It's the data that I've given you, but it's in electron volts. I've converted it to joules because this electron here is basically equal to the charge on an electron, right? Which is 1.6 times 10 to the negative 19. So multiply with 2.16, you get the energy in joules. So for ejection of photoelectrons, you want to make sure that the energy of the incident radiation is greater than the work function of the material. Okay, so this is a work function of the material they've given you here. So what you have to do is calculate the energy of the incident radiation. Now let's go ahead and do that. We know the wavelength of the incident radiation. This is it. Now the energy of the incident radiation according to our equation is HF, right? But what is frequency? Frequency is speed of the radiation divided by the wavelength. So we can transform this equation to look like hc over lambda. So this equation right here, you can replace it with hc over lambda, okay? So hc over lambda means that we'll use a Planck's constant, which is about 6.62 times 10 to the negative 34. Multiply that with speed of light, right? In all electromagnetic radiations are propagated at the speed of light divided by their wavelength, and the wavelength here is 5.8 times 10 to the negative 14. You realize that the answer there is 3.424 times 10 to the negative 12 joules. And notice that this is bigger than your work function, which is 3.45 times 10 to the negative 19. In fact, 10 to the negative 12, 10 to the negative 19, this guy is way smaller. So yeah, the energy of the incident radiation is bigger than the work function, and so photoelectrons would be emitted. Perfect. Hope you learned something, guys. Let's move on to episode 5.